So the next speaker will be Danwei Wang. He should be online. Danwei Wang is professor at in the School of Electric and Electronic Engineering at NTU, Nanyang Technological University in Singapore. He's leading the ST Engineering NTU Corporate Lab. His research interests in robotics range from robot active perception to multimodal sensor fusion, robot autonomy, control theory, and its application. He's a IEEE fellow and serves as chairman, treasurer, and member of the control chapter of RAS chapter in IEEE RAS chapter in Singapore. So today, Danwei Wang will talk about multimodal perception in adverse weather conditions. Please.
Thank you, Philip. Hello, everybody. And as I mentioned this morning, I couldn't come to the workshop, unfortunately. So I present something on this through this internet. So what I'm going to discuss is multimodal sensing for all weather conditions or for intelligent systems. The background you see is Singapore, and I hope that you can join us in Singapore sometime. And so we are going to have an event by the end of this year, ICAF. So I myself, and I have done quite a bit of work in multi-domains, including diagnosis and prognosis, and robot navigation and control, intelligent transportation systems, and multimodal perception. And multimodal perception is more recent work. So today I'm going to focus on this particular portion. In the past few years, I have been working with multiple agencies in Singapore and multiple companies. As you can see that we get some funding from this NRF. This is Prime Minister's office funding. They normally support some domain-specific robotics program. So we get this funding from this NRF, and we have been working with, say, this ST engineering on this intelligent part of these autonomous systems. And we have done this for the past 5-6 years. And we have developed many algorithms like robot navigation, vehicle perceptions, and pedestrian detections, and then their trajectory predictions. We also have done these ITS, Intelligent Transportation System, and for some of Singapore's congested area. One project we did was Changi Airport. And then more recently, we have done, we are still working on this project on this autonomous environmental service vehicle. And we are working on the whole set of solutions. And basically, it's a deep tech enabled solution for the future generation of environmental service vehicle. And then we are working with Continental on this last mile delivery robots in all weather conditions. And also we are working on these aircraft push tow, and this working with a local Changi Airport now, and try to improve the safety and eventually progress to autonomous operations. So you can see that all of my work were outdoor applications. And then for these outdoor applications, once in the industry, outdoor industry setting, one thing is for sure, they always ask is the operation has to continue, no matter what weather. It's a rain, different rain, and then in the foggy and smoke and in different weather conditions, the operation cannot stop. So we have researchers all over the world have developed a lot of techniques and then the technologies for operation in pretty good weather conditions. And then when the weather is not good, and there is an important challenge. There is a challenge because the information feed into the robot is not reliable, it's not clear. So the whole system will not be able to function. So that's why we, recent years, we focus on the sensor perceptions in all weathers. So when we are working on this, autonomous environmental vehicles, and then we use a multiple type of sensors, and then they are mounted in all over the vehicles, and then we need to fuse all this information to get a better perception of the environment. So that's why we get a motivation that we want to develop a sensor suite and develop some basic technologies associated with one sensor suite, and then provide the input to the robot in outdoor applications. And so in doing so, we are able to promote the upgradation and iteration of intelligent perception industry. That means sensor itself, there is a huge demand for different applications. Besides robots, there are some surveillance, there are many applications. Now, 5G and V2X are very popular, and then these communication means actually can support sensors which demand higher bandwidth, okay? And then, so we also, at the same time, we want to train a lot of manpower. So in terms of perception, actually, there is a huge demand. And this two lines shows by mid of 2023, advanced perception function will become a standard configuration of a collaborative robot systems. And so this is a surely important application for when we deploy large fleet of vehicles, and then we need perception to make it possible to for higher productivity. Also, the market for smart sensor is very good. And then the report says it's going to be $105 billion by 2027. And so for perception, for autonomous system, basically we have 3 layers of process. The first one is a perception layer. The second one is a decision layer. And then we have an execution layer. So for the perception layer, that will include the sensor calibration, environmental perception, and data fusion. Then when we have all these come to some correct perception of the environment, then the decision will be made, and then we can make a right judgment and plan the path and then send to the motor for execution. And currently, actually, there are a lot of sensors available in the market, LiDARs, cameras, and all kinds of sensors. But actually, how to fuse them together, and actually, is still a bit lacking. And because situation demand correct perceptions in all situations. Like in this case, when we have a mobile autonomous systems, we normally plan the, we train the, we code the perception to understand the lanes, the road, and so forth, the traffic. But if there is a fallen tree, and the tree is could be very arbitrary shape, and they are lying on the ground in a very funny way, and very unpredicted way. And you can see that in all other weather conditions, the situation just unpredictable. At nights, and then the simple method becomes very complex. When there is rain and then there's some water on the ground, you can see that. And this will cause a lot of problem for autonomous systems, for perception in particular. With a correct perception, then probably decision making will be easier and the execution will be able to follow. So there are a lot of challenges we list here, and then that is due to the perception in all different kind of weather conditions or situations. Also in the smart urban traffic conditions, and then we have a lot of systems based on the 2D LiDAR images. But with this, and then actually the correct perception is not quite ready, because occlusion happens all the time in this high traffic situation. So we need to have some depth information to actually improve the tracking of these vehicles. Okay, so now we are going to discuss a few results we have achieved. The first one is actually we developed the sensor suits and like 3 cameras, and then the combination of camera and LiDAR, and they are mounted on mobile vehicles as well as this on the lamp pole, so that we can use for different applications. And here are some examples we have developed, and this is a handheld, this is put on the vehicle, and this is a mount on the building on the pole. So some are just stereo vision based, and some are LiDAR and camera based, and some include thermal camera as well. So with this multimodal sensing, we actually can do quite a few things. For example, at night, we use a thermal camera, which will be able to detect, even though the normal RGB camera will not function at all. So we are still able to do the detection, and then we combine with the LiDAR, we can actually localize. We can create a static map, the environmental map, and localize the individuals in this static map. So we are able to pinpoint their locations very precisely. And now we have developed these, for the first one, we developed a set of technology for this calibration between different sensors, so that in a sensor suit, we are able to put all the information into a common coordinate frame. We also recently developed a technology which allow us to do the calibration of 2 sensor suits. For example, here, we put one sensor suit here, the other sensor suit here. And then these 2 sensor suits, you can see that we just put them on tripods, and they are quite arbitrary. And so this will see the environment from one angle, and then this one see the environment from the other angle. Eventually, we are able to, because of the calibration method is there, so we are able to fuse all these point cloud into single coordinate frame, so we can create this 3D digital twin for any environment. So this is for both static and mobile objects. And then for this outdoor and mobile situation, as we can see, and we put 2 cameras on different, we can have a 1 key stroke for calibration, and then we are able to detect the ongoing traffic situation from 2 different angles. So that will avoid the occlusion situation, because sometimes we do see trucks blocking the view of these small passenger vehicles. So the fused 3D digital twin will allow us to achieve more reliable detection and tracking, and as well as avoid occlusion. Of course, we have developed this capability of doing this nighttime tracking on a mobile platform. We also use the, we are able to allow these detection to be selective. If we want to select whatever you want, and then actually we can just tick whatever you are interested in, then we can define the distance of interest as well. And also we can define what is being close or what is being far with a 3 range. So this is a very close, very safe. This is a very dangerous, this is intermediate. And so we are able to define, you can choose one chair. And then once you choose this chair, and then you detect other objects, and all the distance will be the distance between this selected chair and the surrounding objects. So this is some functionalities we can achieve. We have a chosen person and this chair to be detected in this case. We have developed some results on this rain removal and how to do the perception under the different raining conditions. We also have developed this 2D RGB-based, thermal-based, and then with depth estimation capability, so we can estimate some moving objects, even though with a single perception. We also have done work like in some very challenging situation, like in smoke conditions. And then when we use our sensor suite, we are able to detect reliably on this on the situation behind the smoke. Now here, these two, the bottom two are actually from this thermal, and this is RGB. And then the top two images are actually based on two fusion method we have developed. So you can see that when you use a normal RGB and there's some smoke, and then it won't be able to detect the people behind it reliably. But with a thermal, actually, we are still able to detect people. And so with even under this condition, then you can see that the fusion method will provide much better situation output. And this one, we combine the thermal and this RGB, this thermal, and in the middle is by this LiDAR itself. So in this case, a single modality give us some detection, but they are not reliable under certain situations. So we developed 3 fusion methods, which will be seen here. In actually, you can see the number, how many people are detected. They are a lot more reliable than the single method. So under different conditions, and then the 3 information channel fused together and actually provide us a lot more better this perception results. And then the other work we have done is actually when we use a lot of sensors for this perception in autonomous vehicles, and actually they are the prime sensor for navigation. They are subject to these attacks, cyber attacks. And because for bigger vehicles, and we are looking at the sweeper, which run in the urban environment, and the public safety is a prime concern of the authority, regulatory agencies. So we look at the potential cyber attack on this GPS, LiDAR, and then the steering control and acceleration control. So for these 4 components, they are actually the necessary component for any mobile robots. So these are the key things. So people develop methodology to attack these sensors as well as hijack these actuators. And then so for the GPS, people can use a spoofer to change the position of the vehicle. So the real vehicle is here under attack. Actually, it can you might misunderstand the computer might misunderstand the vehicle position at this location. And so this is they normally do for this LiDAR attack, they normally change the point cloud by replaying the point clouds. So actually, the fake position is different from the real position. So if the vehicle is already in the zebra line with some pedestrian in front, it could understand actually it's 50 meters away from the crossing. So it can keep going, so it can create a disaster outcome. So these are very dangerous. Also, the actuator has been proven to be hijacked, and then this has been causing some highway accidents all over the world. So we look at these few scenarios, cyber attacks, and then we look at a few situations. So one is a denial of service. The other is a data injection. You can see the red line, actually, GPS is supposed to give you this reading continuously, but under attack, and then this suddenly stop the reading. This gives you a jump in reading. The most challenging one is it gives you a continuous changing of reading. So for the LiDAR replay, actually, this will give you a misunderstanding. The vehicle is still in this, even though the vehicle has moved ahead already. So we have done, we have developed algorithms and to detect it. And then here we have done the experiment verification. So without this detection algorithm, when this guy launched this LiDAR replay attack remotely, and then so the vehicle misunderstands its current position and try to go away. And then so he has to brake. But with this algorithm, actually, once he tried to launch an attack, and then the vehicle, the algorithm will be able to detect this attack right away and stop the vehicle. So we have done many tests. Every situation, we have done 20 trials, and then successful, and all of them are successful. And then you can see that for different kind of attack, if they are single attack, actually the detection is very quick, and we get 0 second or below 2 seconds. And these are the average of 20 trials. And then the algorithm was to detect the single sensor attack, but now we make it difficult, and we attack both sensors at the same time. And then so we count on these LiDAR and these GPS as our main information channel. Now both of them are under attack. So, but we are able to detect them, and but it takes a bit more time, and that's all. And we are, they are still very, our algorithm is able to detect all the cases. It just took more time. And we are working now actually to combine these detection algorithm, even though they have a combined attacks. I think time is close to so one thing I want to share is one more thing I want to share. Actually, we use this sensor technology for robot sensor technology to develop this teleoperation. And this, you can see that we have this teleoperation platform inside the laboratory, and then the vehicle is running outdoor anywhere. So we don't have a map, we don't have any information on where this vehicle is going to, but because we are equipped with a very wide field of view, and then the driver is sitting on a motion platform, which is simulate the driver's seat. And then so this vision and this motion platform are synchronized. So he's driving the vehicle with a very good situation awareness. He can see, he can feel, and then he can actually, there is a haptic feedback on this driving. So in this case, he can actually feel the friction between the tire and the ground. So with this, actually, we can achieve this teleoperation in a very high fidelity level. And the latency here is only 190 milliseconds. And actually, by industry standard, 250 milliseconds is actually good enough for teleoperate vehicle, which run at 70 kilometers per hour. And then we are able to make it faster than that. And last week, we actually have a demonstration in one of exhibition in Singapore. And the platform was located in the exhibition. And then the vehicle was running in 40 kilometers away. And we use connectivity by 4G and 5G. And we were able to teleop the vehicle, teleop this vehicle very smoothly. So, okay. So that's all I have for the moment due to time constraint. And then if you have any questions, I'll be happy to try to.
Thank you, Danwei.
Thank you.
So, any question?
Regarding cybersecurity,
Yes.
you have achieved 100% detection on about 20 repeat cases on all the different side channel attacks. So are you confident enough to open up a bounty program?
Open up a what?
Bounty program, like for example, let's say I invent a new cryptographic scheme and I open source it, the algorithm, like Diffie-Hellman, for example, and then I would pay anyone who finds
This is our plan, and we have achieved this one, and we are talking to this local authority, LTA, which manage all the AV testings. Actually, originally they have test. They call it milestone 3, and the cybersecurity of autonomous vehicle will be one of the test items in that M3. So we are talking with them. Originally, the cybersecurity was about the communication for the computer, about these computer networks. And then now we have the last layer, one more layer of cybersecurity. And we looking at the data, the sensor data, and then see anybody is messing up with our data. And then we can isolate that particular sensor. And then so we stop that sensor. And then if other sensors are okay, then the vehicle will continue. Yeah, and we intend to make it commercial, and then it will become a commercial product. I hope it can be done soon. Yeah.
Thank you.
Thank you.
Thank you for the talk. I also have a question about the cybersecurity aspect of your work. In your tests, have you identified the weak points in your architecture, or were you just quote unquote injecting the false data through, let's say, through your own access points?
Actually, we do not know how the cyber attack will come in. They might come in by breaking the communication channel. They might come in by vicious software. But basically, eventually, they want to change my readings, mess up with my data. And then we have basically, besides these two sensors, and we have one IMU. And then the IMU, we must have a bit of a redundancy in this sensing to actually detect some vulnerable points. And then some are easier to be attacked, some are less vulnerable to be attacked. So the IMU is in the case of a less vulnerable, and because it's an internal sensor, and then the less, so in this case, we in this case, we use IMU for, say, the double sensor attack, and then they cause confusion. Actually, the two sensors cause confusion, and then IMU provide a third opinion. So after a certain time, actually, we know that these two sensors are not, the informations are not cohesion anymore, and then or three sensors are not cohesion anymore. Then we can decide actually there is an attack here. Yeah.
So
I think you have another question. I probably have missed the point.
no. I just wanted to follow up in order to clarify your answer to myself. So you are basically assuming that the attack for that the sensors are the most vulnerable part of the system, and actually in some way you are certain that the assessment module, which is monitoring the quality of the measurements and the cohesion based on the IMU, will never be breached.
Actually, at this moment, that is the case. This is assumption, but actually you're right, and we should not make this assumption. This is the beginning of, I mean, the work will go layer by layer, and these are four, two sensor and two actuations are the fundamental components of any mobile robots. So we start from these four critical components. And then when these are successful, then we look into any other potential risk. And of course, probably nobody will be able to ensure 100% safe, but what we try to achieve is safer. Right?
Thank you very much.
Thank you.
Another question? Okay, I have one question, Danwei. Did you
Yes.
any work on hyperspectral camera for difficult weather condition?
Say it again, I missed your point.
Did you work any using hyperspectral camera instead of using different kind of camera, for instance?
We have used these normal cameras. So we have used these thermal cameras. So we have used LiDAR.
Yeah.
We have used 4D radar now. And then so all these sensors are under our investigation. I understand there are more sensors available, and then but so far we're using these four type of sensors. Yeah.
Okay. Any more question? No? Okay, so thank you, Danwei.
Thank you.